Welcome to Unit 1.1, Video 8 for Mr. McGeehee's 9th grade biology class at Arizona School for the Arts. This video series follows the biology coloring book of Robert D. Griffin. In this video, we're going to take a look at diffusion and osmosis. Before we begin, take a minute or two to review why water is a good solvent, and see if you can answer this question. What is the difference between a solvent and a solute? As you probably know, the particles in substances are in constant motion because they have kinetic energy. If the substance is a liquid or a gas, those particles are free to move and bounce, rebounding off of each other and off of surfaces in their environment. This makes their direction of motion random, so they're moving in all directions. Diffusion is a description of what happens to those particles when they are grouped together in a high concentration. They'll move. The particles will move from an area of high concentration to an area of low concentration. This happens because when the particles are close together, as they are in a high concentration, there's lots of bouncing. They hit each other and rebound, moving in opposite directions. But there's less bounding when they're in a lower concentration. You can see this by adding a few drops of food coloring dye to a container of water. In the beginning, the dye molecules are clustered in a high concentration, but over time, they spread out. Eventually, they reach a dynamic equilibrium, where all of the particles are spread evenly through the water. Substances can diffuse across membranes as well. Here, the molecules of dye are fitting through small spaces in a membrane. If one side of the membrane has a high concentration of particles, over time, those particles will move across the membrane until there's a dynamic equilibrium where both sides of the membrane have the same concentration. Solutes easily diffuse across the cell membrane, but I want you to think about how this might affect homeostasis. Water molecules diffuse as well. When water molecules diffuse across a selectively permeable membrane, we call this osmosis. If you had a container of water that was divided into two compartments by a selectively permeable membrane, those water molecules would be moving across the membrane all the time. If one side of the container contained a protein molecule, the water molecule would be drawn to the protein molecule, and the water would tend to flow toward the greater concentration of those solutes. This results in osmotic pressure. As the water flows across the membrane, it causes a greater amount of pressure on the side of the membrane into which it flows. So you can think of the osmotic pressure as being higher when there's a higher concentration of a solute. For example, if we took a solution of 2% sucrose and put it into a bag and placed that bag in distilled water, what we would find is that the water molecules would be moving at a higher rate into the bag than out of the bag, and as a result, the bag would expand. If we put the solution of sucrose into a greater solution of sucrose, then what would happen is the water would be flowing out of the bag at a higher rate than water flowing in, and the bag would shrink. It's only when the solution of sucrose inside the bag is the same as the solution outside the bag that we see the bag retain its shape. And this happens because water is flowing into the bag at the same rate as it is flowing out of the bag. Tonicity is a measure of the relative osmotic pressure that's caused by water flowing from one side of the membrane to the other. We call a solution hypertonic when it contains a higher concentration of solutes than the solution on the other side of the membrane. When both solutions have an equal concentration of solutes, we call them isotonic. We call a solution hypotonic when it contains a lower concentration of solutes than a solution on the other side of the membrane. This affects living things. If we take a blood cell and put it into an isotonic medium, water flows into and out of the cell at approximately the same rate, and the blood cell is able to maintain its correct shape. However, if it's put into a hypertonic solution, water will flow out of the cell and it will shrivel, causing the cell to die. If we put a blood cell in a hypotonic solution, water flows into the blood cell, causing it to expand and eventually burst. Plant cells encounter changes in tonicity more frequently than animal cells. How do you think plant cells are able to deal with those changes? That's the end of this video. Please complete the corresponding review questions and be prepared to show me your notes in class. Thanks, and have a great evening.